Hello, and welcome to another video tutorial in ANSYS Workbench. In this tutorial, we are going to look at the plastic deformation of a curved beam. So here's our solid member, and we are going to fix this side of the member and apply a moment to this side of the member and determine the maximum moment that can be applied before the system becomes a plastic hinge or fully plastic. This is very similar to the problem defined in the textbook Advanced Mechanics of Materials, 6th edition by Arthur Baresi. So to begin with, we start with opening ANSYS Workbench, and we drag and drop a static structural module into Workbench to the project schematic. Then we double click on engineering data, and I'm going to use steel for this, so I can just click on the steel here. And if I want to come to engineering data sources, I can click on engineering data sources here, and I can minimize these windows. And then you can see that structural steel is the default down here, and I can slide it and move it where I want to. And these are the properties that are in the structural steel. If I want to go back and use the structural steel that I have already created, I can come back to Filter and unclick Engineering Data Sources and click on my structural steel. And this is the structural steel that I have already started to develop. And you can see here that I have inserted a bilinear isotropic hardening. And you do that by coming over here to the plasticity models and then click on it and drag it and drop it to the properties outline window. This I used initially, and what you do here is you can click on the tangent modulus type and select plastic. That's the default. Then you enter in the yield strength, and this should match the yield strength that you have down in the bottom here, tensile yield strength at 2.8 e to the 8. And then for an elastic, perfectly plastic material, you enter in a tangent modulus of 0. This tangent modulus is essentially the slope of the stress strain curve once you have passed the yield strength. And so for an elastic, perfectly plastic material, we want that to be a flat line, and that 0 gives us that flat line. I've also entered in a multilinear isotropic hardening module. And again, you do that by just coming and dragging the member from, when you click on structural steel, drag the item that you want and drop it into the properties outline window. And on the multilinear isotropic hardening, you can see it's not crossed out. So this is the actual one that I am using. If I wanted to come back and use the other one, I could simply click on it and say delete on that one, or come down to the multilinear and right click and delete that one, and then it's gone. So inserting that back in, I can come to multilinear and drop it on, and you can see it shows up. It has some question marks. Here's the table data, so you click on tabular data. I'm going to enter in a temperature of 20 C, and then you define your plastic strain module. So at a strain of 0, I'm going to set the yield stress to be 2.8 E to the 8 pascals. Then I come and at a strain uh, of 0.1, I'm going to have this occur at the yield strength as well. So I'll type in 2.8 e to the 8. Now I can put one more point in at a very large strain, so I'll put in a value like 5 and come here and go 2.8 E8. And now I've got a little bit of a table here for my multilinear isotropic hardening. You can also come over here and instead of deleting it, you can just check mark it or uncheck mark it. So you can see that by placing a check mark in this column, it wipes out that module. So since I'm going to use this multilinear analysis and the multilinear model that has been plotted here, I'm going to go ahead and uncheck that. Then what you want to do is make sure your other properties are set how you want them. Oftentimes you won't have a compressive ultimate strength, and you may want to enter that in. And other than that, that's about all we need to do in terms of the materials. So I will come up to engineering data and close that window. And you can see now here that I need to resolve or update my model. And so I just click on update, and that update will go and refresh all this screen and give me the data and the solution that I need. Before we do that, in general, we need to create our geometry. And to create our geometry, we double click on geometry and ANSYS will open up ANSYS Discovery. And we need to build this beam. So to show you how to build that beam, I'll delete this one and rebuild it. So to delete the beam, I can come over here and right click on solid and come down to delete, and it deletes the body. To create this body, I will come up to sketch mode, and the first thing that you want to do is make sure that your units are correct. So if you click the file and then come down to settings and then to units and display, you can see that I'm using metric units with a length in millimeters, and that's what I want to use. And that kind of sets up the default for all new documents. Now for the document you're in, what you want to do is come down here and click on this icon, and it sets the model units that for the specific model that you're dealing with. And so here I'm using, again, metric. Now we're ready to start to sketch, and it's often good to see the sketch plane. So if you click on sketch mode in the sketch plane, you can see these sketch planes. For this model, I actually am going to switch sketch planes to the XY plane. Then I'll sketch the cross section, and then I'll rotate it about the Z axis. So you can see as I move my cursor around that the sketch plane is changing planes. So I'm going to click on the XZ plane, and then when I go to rotate it, I can rotate it about the Z axis. So I click on that, and now I can come up and click on plan view, and I'll look down the Y axis for my plan view, and I'm going to zoom this in with my middle mouse button, control middle mouse button to move it, and I'm going to come up to my geometry, and the first I'll click on the rectangle, and I'm going to define this rectangle from the center. So I'll come over here and click on draw from center, and then I click the center, and this starts to expand. I actually want this length to be 100 millimeters, so I type 100 and then tab, And now that directly comes down to the next dimension, and I'm going to make that 20 millimeters. So 20, enter. And there's part of my cross section. Now I'm going to come back up here to rectangle, and I can create another rectangle. This one I'm going to start 10 millimeters up here and come down to here. And you can see that that's already 40 wide because I'm still on the draw from center. So I'll hit escape there, and then I will click on this icon here, and I can draw again from center. And now if I come over and click on not draw from center so that I unclick it, I can come up here and click and come down to 20 centimeters, or I could type that in. Go 20 tab, and now this one I want to be 100 millimeters as well, so I type in 100 and enter. So there's the cross section to that point. Now I want to move this so that I can rotate about the z-axis. So to move this, I'll come up to move, and then I will click on these lines, click the first one, then control click, or I could box select and select all of them at the same time. Now that I have all of them selected, I can come over here to my cursor and control click to move that, and then grab my arrow, and I can move the whole thing, and I can enter in the distance I want to move this, and I'm going to want to move this 70 millimeters. So I'll click 70, enter. And now it's been moved that far. Now I can middle mouse button and rotate around, and I can start to look at rotating this cross section about the z-axis. So to rotate it, I'm going to come up here to the pull command. I'll go on the left click on this body and control left click here. And now that I'm on pull, I want to make sure that I pull this around a rotation. So when I let off the control button, these icons will show up, and I click on the revolve icon, click on that, and then I come over and I click the axis that I want to rotate about. Now I can come over and rotate my body, and I will type in 180 degrees, and my cross section has been created now. I can scroll in and out. I can orient this in the z-axis, along the z-axis, and so that's the body that I'm looking at. And you are ready now to save this and go into ANSYS Workbench. And coming back to here, now I can double click on model and open up my model, and I will be in ANSYS Mechanical. One other thing that I've found is helpful when you're doing this particular problem is to come in and round some of these edges so that you reduce the stress concentrations. And on this particular one, if you come to the pull command and then click on this line, you can click on it and rotate the whole thing around. If that's not what you wanted to do because you selected the face instead of the line, just hit escape and then come back and click on the line. And I'm going to get the line in a little better position. Then when I click on it, I can see the line, and I can scroll it in and out, and I can type in the dimension that I would like this to be. I might set this at a radius of 5 millimeters. Then I would come and click this line as well, and again you got to make sure you get the right line. So click on the line, hit the arrow, and then you can move it in, and I would type this in as 5 millimeters as well. On this particular problem, I rounded these two edges and then the equivalent edges on the other sides of this same beam. Then you can bring that into ANSYS Mechanical. So clicking on Mechanical, this is the body that I have, and you can see that these edges have been rounded. I did not put a fillet in between here, but you certainly could have to reduce some stress concentrations that will likely develop in this region here. So the next thing that you'll do is you'll come over to geometry, and you'll make sure that your system came in and that you're using the material you have defined as. Uh, Then you can click on materials, open up this window or drop down menu, click on your structural steel, and what you want to double check is that your multilinear isotropic hardening has been shown here and that this is your material model. You can click on this graph and it will show you the data points that you entered. And so here are the 3 values that I entered. Those look correct for my model. And that's all we need to do to this point. Now we're ready to start to look at how we're going to define our model and mesh it. And so if we click on mesh, we can see the mesh that I developed. And this mesh has been developed, and it came up with these tetrahedral elements because of these rounded edges. If you don't round the edges and chamfer the edges, then you will get a really nice brick mesh. You can see that on my mesh I came to sizing and I increased the resolution from the default value of 2 to a value of 6 to obtain this mesh. Now we're going to load this into the plastic region, so we want to make sure that we have at least 3 elements going across the width. This would be better if we even had more elements. So if I was doing this problem not as a tutorial and needed really good results, I would use a finer mesh than this where I'm going fully plastic. For now, this is the mesh that I will use. So you can just go ahead and mesh it. And now when we look at how we're going to load this thing, what I'm going to do is place a fixed boundary on this face of the beam. And I'm not going to use a completely fixed boundary. I'm going to use displacements 0 in all directions. So I'll come over here to static structural, click on that. It brings up this environment window, and I can come to displacement, click on displacement, and that will come over here and drop in this displacement. You can see that I've selected this face here, and I have set all the displacements in the X, Y, and Z directions to be 0. So that should constrain my body enough so that I can get a solution. The next thing I want to do is consider how I am going to apply a moment or a load to this cantilevered curved beam. And I guess it's not cantilevered because we just fixed displacements here. But I can apply a moment here. I can apply a force on this face. I can apply a displacement. We know that in general, you typically get better results when you're going into the plastic range by applying displacements. Those answers usually converge better than they do by applying forces and moments. However, in this first example, I am going to apply a moment. So if I come up here to loads, I can click on moment. It will come over here and drop my moment in. I can click on that. You can see that I have selected this bottom face, and I then clicked on components instead of vector, and I entered a moment about the z-axis of 3.5 e to the 7. I can click over here on the z-axis and look at my beam straight on. So if that's all that you want to do for loading, then we're done. Coming up to analysis settings, when we're doing a plastic model, I actually like to turn auto time stepping off and insert the number of substeps that I want it to break the load into. If you leave auto time stepping on, you have the option to enter in various controls. So if I turn it on, you can see that I can enter in the initial substeps, minimum substeps, and maximum substeps. But with auto time stepping on, ANSYS does its own thinking. And even though you have prescribed these values here, ANSYS will break up the load into the steps it thinks are best. So to have complete control, you need to turn the auto time stepping off and then set the number of substeps that you would like to have. Since I'm only applying one load, I keep the number of steps up here to 1. Then since we're going plastic, you want to make sure you come down to large deflection. Click the drop down and make sure large deflection is turned on. These other commands or changes in these other commands are not needed. You can open up the nonlinear controls and pretty much leave these as program controlled solutions. Under analysis and data management, there are no real changes that you need to make there either. So with those changes in and settings in analysis settings, we're ready to go ahead and define the output that we want to have. So we now have our solution. One thing I just wanted to emphasize again is that when we click on equivalent stress, we have come down here to display the element mean. If we come back and use average results, this lightning bolt will turn yellow, but when I click on solve, it will update quickly. And when I click on equivalent stress, you can see that the values now are much higher than the ultimate or the yield strength. And this is because ANSYS is extrapolating the Gauss values, the values computed at the Gauss points. And these Gauss points are internal locations in the element, and they're used for calculating stress and strain through numerical integration. The nodes, they're used to insert forces and moments and boundary conditions, and they're used to calculate the displacements. So when the stresses are calculated at the Gauss points and then extrapolated to the nodes, this is where you get these higher values that are not necessarily representative of what's going on in the structure. So make sure that you come down here and on the display, you click the drop down and use elemental mean. This command down here that we talked about, the ERESX, no, that's a command that lets us copy the integration points directly to the nodes rather than extrapolating them. So the values are not extrapolated from the Gauss points to the nodes, but they're copied directly to the nodes, giving us a better result or a better representation. So when we come here to look at equivalent plastic strain, we can see that most of this material, if we come up and click on probe and move our cursor over the structure, most of this material has not had plastic strain occur. Down here at our boundary, we get a little bit, and over here on this edge where we applied the moment, we get some. However, we know that our model has developed a fully plastic hinge, again from our load deflection plot. So even though our our equivalent plastic strain plot shows that it is not fully plastic, we've hit that load based on a force or load deflection plot. ANSYS is not able to compute plastic strain unless your stress goes over the yield strength. So where our equivalent stress is essentially at the yield strength, ANSYS does not compute that as plastic strain. And so using the plastic strain to see that you have completely gone plastic is not effective and is not the right way to do this. The other thing you can do is enter a stress tool. And on the stress tool, if you click on it, you can see that the theory I'm using is maximum equivalent stress. And then I'm using the tensile yield for the material. And when I click on safety factor, you can see that throughout most of the body, the safety factor is greater than 1. And only at a few hot spots, these red hot spots, would our safety factor be less than 1. So again, this is very misleading in that it shows that we still have a large safety factor and we haven't failed, but The telltale result is to come down here and plot the load deflection curve and see that we cannot apply any more moment without just gathering extremely large displacements. So this was based on this load condition. We got a load or a maximum moment of 3.5 e to the 7. And you will note in the solutions for the Baresi problem, example 9.8, the hand calculations gave a value of about 3.3 e to the 7. So this matches the hand calculations for a curved beam very well. We will now go ahead and look at some of the other loading conditions and investigate those results. So in another loading case, I inserted a remote displacement, and the remote displacement is about a remote point. So what you need to do is come up to Model, right-click, Insert, and then come down until you see Remote Point. Click on Remote Point. That will insert a remote point right here. You can click on this and click on Remote Point, and you can see that I placed that remote point at the center of the beam. Now I can come up and click on Solution, or excuse me, Static Structural, and then come to Supports and click on Remote Displacement and insert this remote displacement. And now when I click on remote displacement, you can see that the scoping, I have a geometry selection, name selection, but I'm going to put it at the remote point. And then I click on which remote point I want, and I only have one of those, and I left it named remote point. So I'll put the remote displacement at the remote point. Now all of these things here are grayed out because I've solved the problem and I have a solution based on these values here. Note that I'm using a global coordinate system, and I have placed this remote point at the 0, 0, 0 position. So right at the center of the beam again is my remote point and the location of where I'm going to put this remote displacement. Now I come down here and type is set for remote displacement, and I can set all of these boundary conditions. I have set everything to be free except for the rotation about the z-axis of 12 degrees. Note that I also set it to rigid from deformable so that the face remains as it is now. So when you do that, you'll get this picture here showing your remote displacement acting about your z-axis at the centroid of your body. When you come over here and solve this, you will note that I got a solution on equivalent stress, equivalent total strain, and normal stress in the y direction. I did not converge to a solution on any of these other components. So if I click on equivalent stress, you can see that much of my body now has reached the 280 yield strength. Some of this out here is shown to be less than that. You can see that right around the joint where the two cylinders kind of come together, I have red all the way around. So this looks like it's pretty close to a plastic deformation based on just the stress. If I come down and look at my load deflection plot, I can click on the outline selection and make sure that I have my moment reaction and my directional deformation still clicked. And you can see here in this plot that as I have increased my moment, it's still increasing, and it is increased to a 4.7 E7, which is significantly higher than the moment we had before. And then when we get down here to this point, all of a sudden we have a huge jump. And that huge jump indicates that we can't apply any more moment, that we have hit our plastic limit. If you click on equivalent stress again, you can see that my model has hung up, so I will need to close out and come back in. So now I'm back up. I can come back up here and click on equivalent stress, and you can see that the angle has been taken from the center of curvature here. And so here are the displacements coming around in a radial direction based on the center of curvature. So if I come back down to stress tool and look at the safety factor, again, you can see that my safety factor doesn't make a lot of sense. Down here, I'm essentially less than 1 for the minimum safety factor. My maximum is still very high, but this does not really help me determine plasticity until I get to the very end here and I see that there's a sharp jump down to 0 in all of the safety factors. I can also click on equivalent plastic strain and these other quantities. Again, if you look at the equivalent plastic strain, you can see I'm coming along and then I have a very large jump. If I look at the normal elastic strain, you can see that I've hit a maximum and then I also have this jump. So I can come here and I can click on that jump and I see it's at time step 0.82. So if I come back to my moment reaction and scroll down here until I hit 0.82, I can see that my moment about the z-axis was minus 4.7 e to the 7. And so that would be my fully plastic moment based on the moment being applied from the center of curvature in this beam. And that number was quite a bit different than placing the moment here. This moment might be more realistic in this model, but to match theory, the moment applied right on this face matches theory better, and that's why our answer before matched the theoretical results and the hand calculations better.